Okay, so let's get started here. So big reminder that we have a test on Wednesday. And so I think it was Friday maybe, I emailed everybody kind of a list of what is going to be on the test. There's still a few things we haven't covered, which I have in bold there at the bottom of topic 5, which include 2 types of calculations, and I'm going to show you how to do them today. That's going to be most of the topic of today's lecture. So hopefully you've had time to review some of those things. Like I said, the calculation parts we haven't done. The calculations themselves aren't too difficult. The worst part is the conversions, the metric conversions. So for example, converting from megaliters to cubic meters and those kind of things. So just understanding the conversions, I find, is kind of one of the more difficult things that people get a little mixed up with. So let's dive right in. And I guess the last thing to say is the format is not going to be any different than the other tests. So combination, multiple choice, short answer, and calculation type questions. So let's talk about pressure. So pressure is basically the amount of force that you get per area. And if you take a look at the units, maybe you remember from high school science, you know, there was a Newton. The Newton is a measurement of force. And so area, of course, in the metric system is square meters. So a Newton per meter squared actually has its own name, and that's called a Pascal, named after a physicist. I don't remember his first name, but his last name is Pascal. It's a small unit, so often a little bit more useful, we use kilopascal in the metric system. You've probably heard of pounds per square inch. That's a pretty common imperial measurement. So I think, like, for example, if you get your tires filled at the garage or do it yourself, the units are usually in PSI. I think we're pretty typical. I'm just trying to think. I just feel like I did my vehicle tires not too long ago. I'm trying to remember what the recommended pressure was. Maybe it was around 35 PSI for my tires. So those are usually the most common units for pressure. There are many units for pressure, though, out there. And so you may have heard of, like, atmospheres or bars or millimeters of mercury. There's torr, and you can see there's a whole bunch on this list here. And unfortunately, with pressure, sometimes it's kind of an industry thing, right, in terms of what units they might use, or even a geographical thing. So like I said, the metric unit is the Pascal. That is kind of the best metric unit to use, or kilopascal. But you may, in your travels, see some of these other ones here. In this class, we're going to be using kilopascals. And that is that's kind of where we're going to be at. But like I said, you may need to learn how to convert between these things someday. So what we're talking about today is something called hydrostatic pressure. And that basically means how much pressure is in some water that's in a system. And that's usually based on how much water is in that system, and it actually has something to do with height. So you can see in this case here, what we have is a little pressure gauge, and you can see in the first system there's a little bit of water, and then there's a medium amount, and then a large amount. And as the water gets deeper, the pressure is going to increase. So this is our first formula that we're going to learn. I think I have it on the next one of these next slides. But basically, like I said, this has only to do with depth and not to do with quantity. So I want to show you these ones here, right? You've got, in our first box, it's 1 meter deep, and it has 9.8 kilopascals. In box 2 and 3, they're 2 meters deep, and so they have 2 times that, which is 19.6 kilopascals. Even you can see box 3 is it's fatter, but that doesn't change the depth, so it doesn't change the pressure. Here's another example just showing you you've got all these different shapes of all these different containers, and if they all have the same depth, they're going to have the same pressure. So it's a very, very simple relationship. Just has to do with depth, or sometimes we call it height, kind of just depending on the formula that you're looking at. So this is also showing that A and E are equivalent and B, C, and D are equivalent. So pretty straightforward relationship. The deeper you are, the more pressure there is. Like I said, it doesn't have anything to do with the shape or the actual quantity of water. So there's the formula, and this is the formula that you need to know. So pressure is 9.8 times height. I won't be asking you on any tests to do the imperial calculation, but if you're interested to get PSI, or pounds per square inch, it's just 0.43 times height. Height meaning the amount of water that's above the gauge, or the amount of water that's above wherever you're measuring at. So we'll do a couple sample calculations in a moment here. But like I said, this should be a pretty straightforward kind of formula, and I'll show you what some of the questions might look like. So here's just a simple one, right? It says we have a water tank, and the depth is 3.5 meters. So basically pressure equals 9.8 times height. So that's 9.8 times 3.5. Put that in your calculator. 9.8 times 3.5, and we get 34.3. And do not forget your units, which is kilopascals. So one little tidbit about the metric system, by the way, is the K. You can use a big K or a little k. Both are acceptable for the metric system. So if you have a preference, I know when I write Ks, sometimes I can't even tell if I've written a big one or a little one, just the way my handwriting is. So don't worry about that one. But do make sure you remember to put the units in there. So hopefully that's straightforward. I'll show you what one of the problems will look like in a moment. Oh, I didn't realize I had this typed out, but looks like I got the same answer, so that's always good news. Here's an example with Imperial American units. Like I said, I won't ask you this one on a test, but you can see we've got, we're measuring in feet, right? And notice this one's a little bit more complicated because it tells you how deep the water tank is, but the pressure gauge is not at the bottom of the water tank. And this is a pretty typical kind of thing, right? The pressure gauge is actually 15 feet from the bottom, right? So in this case here, we have to do a little mini calculation along there, and we have to calculate exactly how deep the pressure gauge is. So that would be 10 feet deep, and the formula there is 0.43 times 10, so 4.3 psi. Okay, so here's a little bit more like what one of your questions is going to look like. I'm going to give you a scenario. There's probably going to be a diagram that's going to go along with it. There could be something like a water tower or a pipe system or something like that. And you have to read the question and make sure that you understand what's going on in terms of where the pressure is and all those kind of things, right? So in this case here, you can see we have a tank, some sort of water tank. It's above this farmhouse, it looks like, and it's elevated 50 meters. And the tank itself is full of water up to 4 meters high, right? So what's the pressure at the house? Use our formula. And so what is the height? The height, we have to add 50 plus 4. And then we multiply that all together, and we get 529 kilopascals. Okay, I think I have another one on the next slide as well here. So there's one more. So this one here, we've got a water tower of some sort, it looks like. And you see you've got some information in terms of elevation. We've got the elevation at the water level is 100 meters, and the bottom of the tank is 95 meters. And so we're going to calculate A. We're also going to calculate B and C and D all in this system. So it's just a matter of figuring out what the height is, right? So for A, I think, hold on a second, let me just go down. Yeah, okay. Okay, so let's do A, right? Don't forget our formula. Pressure equals 9.8 times height. So that's 9.8. And if you take a look, the height is, of course, 100 minus 95 meters. So A is going to be 9.8 times 5, and punch that in my calculator, and I get 47.5. Is that right? Did I punch my... No, I got 49, sorry. I felt like I punched a number wrong. 49 kilopascals. Okay, there we go. So the good news about B and C is they're actually at the same elevation, they're at the same height. So I only need to do that calculation once, right? So B is equal to C in terms of the height. So the pressure there is going to be 9.8 times height. So let's actually figure out the height first. Maybe I'll erase that P. So height, in that case, we've got 100 meters minus, there it is, 70 meters. So the height is 30 meters of water above B and C. So pressure B equals pressure C equals 9.8 times 30. Okay, so I'll punch that in and I get 200 and my fingers aren't doing what I want them to do today. Let's try that again. There we go. 294. Hopefully everyone else got that value as well. And do not forget the units. Okay, so that's A answer is right there. B and C is there, and I still have to calculate D. I think I made myself an extra slide with more space. So pressure at D, let's calculate the height at D. So the height at D is 100 meters of elevation minus 55 meters, so that's 45 meters of elevation. So the pressure at D is going to be 9.8 times 45. So 9.8 times 45, that's 441 kilopascals. Okay, hopefully that's pretty straightforward. Like I said, the main thing is just reading the question and making sure you're calculating the height properly. I think last year I had a house and there was a toilet on the second floor, and I think I mentioned that the second floor, something about the second floor being X number of meters or something like that, and people didn't read that part of the question. So sometimes with pressure, because it's directly related to height, sometimes people just use the height to say that's the pressure. And the term for that is pressure head, right? So somebody might say there's 3 meters of pressure head, or there's 7.3 meters of pressure head. And it's understood you can multiply that by your 9.8, but that's just kind of how the terminology works. It's sometimes just people talk about the pressure head, right? I mean, if you're into scuba diving, for example, pressure calculations are an important part of figuring how long you can be under the water without experiencing effects. And they never calculate the pressure. They just talk about how many feet of water you're in. Are you in 80 feet of water? Are you in 30 feet of water? And so on. And if we want to use metric, we'd use meters, of course. So that's what pressure head is. So here's just a couple more calculations just to get us some practice. So here's one. It says we have a pressure gauge is 2 meters from the bottom of the tank, and it reads a pressure of 75 kilopascals. So what is the total depth of the tank? Okay, so we got to think backwards in this case. So remember our formula is P equals 9.8 times H. So we're going to retransform that formula so that we can figure out height. So pressure divided by 9.8. And so our pressure is, of course, 75 kilopascals. Here, let me make that a little neater. There we go. 75 kilopascals divided by 9.8. Uh-oh, I erased my P. There we go, better put that back. Okay, and so I get 7.7 meters, if I do that correct. Let me just double check on my calculator. Yeah, 7.7 meters. But that's not the end of the question, right? This just tells me what the pressure is at the gauge. Read the question. It says that the pressure gauge is 2 meters from the bottom of the tank. Okay, so the tank, 7.7 meters plus another 2 meters. So 9.7 meters would be the correct answer for that question there. Okay, so like I said, these are just kind of sometimes word problems, and the math should be straightforward. It's just a matter of thinking about what you're looking at. Sometimes when I do questions like this, I draw a little diagram like this along the side, and I'm like, okay, we've got the gauge here, and I've got 2 meters, and then I'm figuring out the height here, and so on. And so often that's how I do these kind of problems when I'm trying to figure them out. I think I have another question here. So just stop me if anybody has any questions, okay? Here's another one. It says that we have a pressure gauge on an open tank of water at a point 0.5 meters from the bottom, and it registers a certain amount. So what is the pressure head at that point? And then the total depth of the tank, right? So pressure head, I'm just calculating height, right? So here again, we have a little tank of water, and the gauge itself is 0.5 meters. And then I'm figuring out the amount of pressure there, right? So our formula, rearranged from the last slide, was pressure over 9.8. Okay, so that is 88.2 divided by 9.8. So 88.2 divided by 9.8, and I'm getting 9 meters. So that's 9 meters of pressure head. 9 meters of pressure head, and then the total depth, I just have to add that up. So it's 9 plus, what was it, 0.5, so that's 9.5 meters. Okay, so take a look at the practice problems that I have on Moodle. I know there's a few others in there, and if you can get these, no problem. It should be some easy marks on the test. Okay, so a little bit more about water pressure, and then the harder part I want to talk about is the continuity equation. We'll get to that in a minute. But some things to know about how do we measure pressure, right? And especially with water pressure. So kind of a classic way that this is done in some areas is called a Piezometer Tube. And if you take a look at what's going on here is basically you have some water, it's flowing through something. It looks like a pipe in this case. And basically what happens is a small tube is measured and you see how far the water goes up the tube. This is kind of an old, cheap, classic way to measure pressure. And of course, the water is not going to go up forever. Eventually, due to gravity, the water can't go very high. Now, if this was a high pressure thing, like if this happened to your, like say, garden hose, you probably know the water sprays all over. But for low pressure systems, groundwater and things like that, this works relatively well. You get a measurement of how high it goes. That tells you the pressure head, which you can convert directly to pressure. I haven't seen these used other than people have mentioned them a few times. But if anyone ever sees these in their travels, I'd love to hear about it. But now you know what one is if you ever hear about it. Like I said, one problem with these is that if the pressure is high, the water just squirts all over the place. Here's another diagram of one here showing one that is, I think this is being used to measure the water pressure in an aquifer. And there's little meters in there to show how high the water rises. Like I said, I'm not entirely familiar with the operation of these, but apparently they're pretty commonly used in some systems. Sometimes the problem is, like I said, you've got this water squirting all over the place. You can sort of actually reduce that by not using water, but you can use mercury instead. Mercury is much more denser and heavier, and there's a direct conversion between the height of the mercury and the actual pressure. Same idea, but anyway, I won't be asking about nanometers on the test, but if you ever, if you hear about one, you know it's something with mercury. So there's a sample conversion, by the way. So probably what you will see in your travels, though, are these pressure gauges. And there's different engineering principles behind these pressure gauges. A lot of them will have, as the water flows through it, Usually there's some sort of spring or coil or something like that that gets pushed, and as the coil or spring gets pushed or compressed, that leads to a reading, and the reading is either going to be analog, as you can see on this particular meter here, or it's going to be digital. And if you're in luck, it's in the right units, right? Because of course, you know, you can see that particular meter has both PSI and kPa, and sometimes you know, you need one or you need the other. But thankfully, that's why we have the internet to do conversions relatively easily. Okay, so the other thing I wanted to talk about today is something called the continuity equation. And this is basically something that describes water flow through a system. And so you can see we have three variables. We have Q. Q is quantity. So quantity is volume per time. And in the metric system, we're using cubic meters per second, or you could use liters per second, or you could use megaliters per day. And this is the thing that gets complicated with this particular equation, because you may be asked to calculate megaliters per day, or maybe cubic meters per second, and depending on the units you're given, there's a little bit of a conversion somewhere in the middle. So I'll bring you through some of that in a minute. I have a couple of sample questions for you. The other units are velocity, right? So velocity is meters per second. I mean, I guess you could go kilometers per hour or something like that, but usually we use meters per second. And then we have A, so this is a pipe. So a pipe has an area. And so you just have to remember, how do we calculate the area of a circle? Anyone remember how you calculate the area of a circle? That's the one, yeah, pi r squared. So you just got to remember that one. That's like, I don't know, grade 7? I'm not sure, somewhere in there. I know I'm asking you to reach back in the depths of your memory, but it should be a pretty straightforward calculation. So the units on these things, like I said, depending on what you're looking at, the typical units are cubic meters per second or megaliters per day, just depending on the system, right? If you're a city, you're probably thinking about megaliters per day, right? We're talking about massive water mains and those kind of things. If it's a smaller system, probably cubic meters per second is a bit more common. So one note on this, the V is a small v, right? You probably know that big V usually represents volume. So a small v, and often what I do when I write my small v's is I write them kind of like that with a little, I don't know what that's called, a little wing on it to show that it's a small v. And but just so you know, right, that try to avoid the big V on this. So let's do a couple of sample calculations. Like I said, these can kind of get a little tricky when you're working with all the metric conversions. Okay. So this is asking how much water is flowing through a pipe. So let's just remind ourselves of what the formula is, right? So Q equals VA. So what do we have here? We're calculating Q. We have the velocity. So this here is the velocity, okay? And what we need to do is calculate A. So let's calculate A. A equals pi r squared. Okay. And here's, believe it or not, this is one of the biggest issues people have, is some people can't remember how to convert a centimeter to a meter. Anyone remember how to do that? Yeah, it's that simple, but I think sometimes people, you know, they divide or multiply by 10, or they do 1,000, and that's confusing, right? So 10 centimeters is 0.1 meters, right? I'm just dividing that by 100. So let's punch that in. A equals pi r squared, so pi is 3.14. My calculator actually has a pi button and gives it to like 10 decimal places, so that's usually what I punch in. So if I don't quite get the same number by punching in 3.14, you can try punching in, what is it, 3.14159 or something like that. And 0.1. And what I'm going to do is leave my units in there because I want to make sure all my units do work out in the end, okay? So 3.14, oh, hold on, I already messed up. Anyone see it? Yeah, there we go. Okay, yeah, I was just getting ahead of myself. So this is actually the diameter. Okay, so I got to calculate the radius. So let me just do some erasing. Sorry about that, getting ahead of myself. So D is the diameter, and therefore the radius equals 0.05 meters. So thanks for catching that. All right, 0.05 meters, and then we're going to square that. Okay, so my area, this is what I'm getting. I'm getting 0.00785 meters squared. So that's my area, cross-sectional area of my pipe. So now I just need to punch everything into the formula because I have them in the right units. I have everything in meters and seconds, so I'm happy with that. So let's calculate the final quantity. Okay, so the velocity is 2.55 meters per second, and that's times 0.00785 meters squared. So notice my answer is going to be in cubic meters per second, and that's what we want, right? That's a good unit to have. So I get 0.02 meters cubed per second, and hopefully you do too. Okay, so that one is reasonably straightforward. Just the one little thing, remembering how to do the area and converting the diameter to radius and all those kind of things are the little things that get people tripped up. By the way, another thing to think about these calculations is when you do your calculations, make sure your numbers actually make sense. I know a few years ago I had one of these questions, and I think it was the opposite. You had to calculate the size of the pipe, and somebody ended up calculating their pipe being 26 kilometers in diameter. That doesn't make any sense, right? They had you know, added in a few extra zeros with their conversions, and that doesn't work out so well. All right, let's try another one. So we've got a pipe, and it's a 10 centimeter pipe, and water's flowing at 2.55 meters per second. So here's question 2. I thought I had this on its own. Yeah, I do. I do have some of these on their own slides, so there's space. So question 2, it says quantity of water flowing through a 20 centimeter pipe, flowing at 64 centimeters per second. Okay, so let's work this out. So that means our diameter is 20 centimeters, which is 0.2 meters, and our radius is 0.1 meters. Hopefully that looks like a 1. Trying to make this look neat. 64, so our velocity is 64 centimeters per second. So converting that to meters per second, that's 0.64 meters per second. So I'm just dividing that by 100, okay? We need to figure out our area again. And so area equals pi r squared equals 3.14 times 0.1 meters squared. And okay, thought I had this down here somewhere. I don't see my calculations, so I'll have to do this again. So 0.1 squared times pi, I get, there we go, 0.0314 meters squared. Okay, and so our Q is equal to V A, so that's 0.64 meters per second times 0.0314 meters squared. Punch that in my calculator. And look at that, I get the same answer. I get 0.02 cubic meters per second. That's the same answer as the previous question. So notice in the previous question, I have a smaller pipe and the water is moving faster. In this case, I have a larger pipe, the water is moving slower. That makes sense, right? You have a larger pipe, it can deliver a lot more water even if the water is moving faster. Notice this last part, it says here, express your answer in liters per minute. Okay, I don't have a lot of space for that, but I'm going to try to squeeze it in at the bottom. Didn't leave myself very much space. So here's the conversion between cubic meters and liters, right? So 1 cubic meter is, anyone have any idea? It's 1,000. Yeah, it's 1,000 liters. So we got to multiply that by 1,000, and then we've got minutes, right? So also remember that 1 minute is 60 seconds. So because I don't have a lot of room, I'm going to squeeze all this into one space down here at the bottom. So I apologize for that, not having a lot of space. But I'll show you how I do it. So I've got meters per second. So I do this, the first conversion is, of course, I'm converting to liters. So I want liters instead of meters cubed. And so there we go. That's 1,000 liters per meter cubed. And then I'm going to multiply and change my seconds to minutes. So 60 seconds per 1 minute. And then it goes way down there at the bottom, 0.02 times 1,000 times 60. So I get 1,200 liters per minute. Okay, so I apologize that was squeezed in. I'm going to do another conversion for the next question, and hopefully I have a little bit more space, and you'll see me do that again in terms of converting between, you have to do it all one step at a time, that's fine. If you don't want to do it all step one at a time, you can do it kind of how I did it, but I'll show you in the next question a sample of that. Hopefully that makes sense for everybody. Like I said, if you look at the sample problems that are on Moodle, hopefully that will get you through these. All right, so one more question. This one is the opposite. It's asking you to determine the diameter of a pipe, right? So it's kind of the opposite. In this case, we have 50 megaliters per day. So what I need to do is actually convert that to the useful units, which is cubic meters per second. So I'm going to do that one right now. And I'm going to do it all right here. So we've got 50 megaliters per day. Okay, so first we're going to convert the units of time. Okay, so I'm just going to do it one at a section. If you know how many seconds are in a day, that's great. You could convert a lot quicker, but I don't know that number off the top of my head. So what I'm going to do is convert days to hours. So what I do is I put hours there and days there. And that way my days will cross out. So of course we've got 1 day is 24 hours. So that's going to ultimately get divided by 24. And then what I'm going to do is convert my hours.
Blaine.
Yep.
There's 86,400 seconds in a day.
Yeah, so I knew it was something like that, but I just converted every time just to be so I've got it all make sure it's all there, right? So then you convert hours to minutes, but if you can do it all one step, then all the power to you, right? It's a lot simpler. 1 hour is 60 minutes. That's a 60. And then of course we're going to convert to seconds, so that's minutes to seconds. And 1 minute is 60 seconds. So that's the first part of the conversion. And so if you take a look at that, like I said, my days cancel out, and then my hours cancel out, and my minutes cancel out. I'm going to be left with megaliters per second. So the second part of that, I'm just going to keep multiplying. Now I want to convert megaliters to cubic meters. And by the way, it's 1,000 difference, but what I usually do is convert to liters first. So we've got 1,000,000 liters is 1 megaliter, right? That's what a mega is in metric, it's 1,000,000. But then I want to convert to cubic meters. So 1 cubic meter is 1,000 liters. So if you take a look at that, 1,000,000 divided by 1,000 is 1,000. So the difference between a megaliter and a cubic meter is 1,000. So you can do that in one step, or you can do it in 2 steps like I just did. So if I do all this, so I take 50 and I divide it by 24, divided by 60, divided by 60, multiply by 1,000,000, divided by 1,000, this is what I get. 0.58 cubic meters per second. Okay, so I know that looks like a lot, but it's just a matter of kind of slowing down and thinking about what you're doing, okay? It's really important that you do that. I know sometimes people, they end up multiplying instead of dividing at this stage in various places, which is why you might mess up with the numbers. But so do it stepwise if you have to, right? So think about it, a megaliter down to a cubic meter. a megaliter is bigger, right? And then with time, seconds are longer than days and so on. So it's important that you do kind of, make sure you think about it. And that's why I like to put everything here together so that I can cancel the units. You can see liters are canceled out there. And then megaliters ultimately get canceled out because one is on top and one is on the bottom of the quotient. Okay, so back to the original question, what was I figuring out here, right? I was figuring out, we want to figure out the size of the pipe, okay? So we have our formula, Q equals VA. So ultimately, in this case, what I'm going to be doing is calculating A. So A is going to be Q divided by velocity. So I think I have both of those values now. I have Q, which is 0.58 meters cubed per second. And velocity is 3 meters per second. So notice my seconds are going to cancel out, and I'm going to end up with meters squared, which is good. And I actually end up with 0.19 meters squared. Okay, so remember my area equals pi r squared. So that means that this is equal to 3.14 times r squared. So now I have to figure out what that is. And so that means my radius is going to be 0.25 meters. And then it's asking me for the diameter of my pipe. So I multiply that by 2 and I get 0.5 meters. Okay. So that's the worst that you're going to see on this test. It's one of these questions. All right, so this will be probably 4 or 5 marks of the test because there's so many conversions and calculations. So if you don't get every part right, hopefully you can get at least some part marks. So, but be prepared to do 1 on the test and 1 on the final exam. And then if you're lucky, maybe you'll never see this again. But it's really not as bad as it looks. Okay, I think most of you guys are pretty confident in your mathematics. And I think with a little bit of practice, you'll look at these problems and realize that they are relatively straightforward. And the unfortunate thing in life is we will never get away from metric conversions. We are always converting things, whether it's from metric to imperial, or we're converting between liters and kilograms and all those kind of things. So unfortunately, you're going to have to get used to conversions. The good news is, in the real world, often you can Google the conversions, or things are done automatically in computers. If you're at a water treatment center and the pressure is in PSI and you want it in metric, it's not really hard to do because usually the software has a little toggle where you convert between the units without actually having to do the calculations yourself. But it is important to know a little bit about how to do these calculations. So any questions about that? Like I said, look at the sample problems on Google, and then hopefully you can be relatively comfortable with this kind of question. Yep.
So the indication that we have to convert from megaliters per day to meters cubed per second, because we know that we get our area in meters.
Yes, that's right. Yeah, that's kind of the base units is meters cubed per second, right? Because they're kind of the basic metric units, right? Because you're probably not going to calculate a pipe length in like megameters or something like that, right? So in the end, you can express your diameter in centimeters if you want, but usually when we're working with metric things, often we're trying to get it to that base unit because it's just simpler. And then often, sometimes you might convert to something that's more useful, right? In terms of like you might like centimeters a bit more, and that's fine. But expressing in meters is totally acceptable, right? Okay, so a few other things about this. This is one of the questions. I remember one of the first times I went to one of the water treatment plants, and they're talking about megaliters this and how many megaliters that, and I said to the guy, "How big is a megaliter?" And he couldn't answer the question for me. I was like, "Is it as big as this room or whatever?" And he's like, "I don't know. I never thought of that." And so here's a simple way to visualize this. This is Mac Island, right? And it's got the Olympic-sized pool, you can see, is 50 meters, and it's about 25 meters the other way, and then they've got the little kiddie pool as well, right? So if you take a look at that Olympic-sized pool, right, and multiply it, it's about 2 meters deep by 50 meters by 25 meters. So I can punch that in, right, and figure out exactly how many cubic meters of water I have, assuming my calculations are right. It might not be 2 meters deep, but I was just estimating anyway. It might actually be deeper than that. But anyway, that was just a rough estimate of how much water is in there. So about 2,500 cubic meters, which is, of course, like I said, I can divide that by 1,000, or I can convert it to liters first. It doesn't really matter. But that's about 2.5 megaliters. So I'm trying to remember the numbers in terms of how many megaliters of water are consumed in Fort McMurray a day. I can't remember off the top of my head. I feel like it was 30 to 50 megaliters of water are consumed by the people in this town per day. So is that a lot? I don't know. But that's how big a megaliter is.
That's not common.
Yeah. So I'm not going to do this particular problem, but I just wanted to show you that in terms of engineering and those kind of things, that this can be a very useful kind of equation. So think about these scenarios of all these plumbing systems and water distribution systems where you have one size of pipe and then you have, it's maybe a larger pipe is the next thing, or a smaller pipe is the next thing. So it turns out that the water flowing from one pipe and it flows into the next pipe is actually going to be the same. So what this is showing that if you have two types of pipes here, and the area changes, you can calculate out the new velocity. So spoiler alert, it's going to be faster in the smaller tube because you're trying to squeeze the same amount of water in a smaller tube. Same way, this also works if pipes split, that you're going to have, the total amount of water going in from pipe one is going to equal the sum of the water in the other two pipes. But I won't ask you about doing these calculations on the test at all, but just something kind of for your information. So a few other things about this. You can see this is talking about these hydraulic systems. Again, another formula I'm not going to be asking you about, but there are a lot of variables in these systems, right? So you can see that this is kind of talking about a bunch of the variables that you're going to see in that system, right? In terms of you might have a pressure head, right? So that might be elevation. You're going to have the size of the pipe. And of course, there's not always necessarily water going through pipes too, which can obviously affect what's going on. Probably temperature as well will affect the pressure in a system. So one thing to know, and this is important for this week's lab. This week's lab, you're going to play around with some of these equations a little bit. And this week's lab is not a wet lab. This week's coming lab is the lab has been done for you already. And what it has done is experimented putting water through some different pipes. And the pipes have different lengths and they have different areas. And that's going to affect the flow. And so one thing to note is that when water flows through a pipe, there is actually a little bit of friction with the water and the edge of the pipe. And so the area of the pipe can actually affect the water flow. And of course, the type of pipe as well. You can imagine there are some pipes that are made of like PVC plastics are actually relatively slippery. Now picture something a little coarser like a pipe made out of concrete or something like that. And so different materials of pipes are going to have different effects on the water as well. So this says here, the flow of water is not the same over distance because the resistance of the pipe reduces the flow. So if you take a look at this system, just go back, there we go. If you take a look at this system here, we have a height or a depth of water. And if there's two gauges there at P1 and P2, and they're exactly the same because the depth of the water is the same. In fact, you can see we have piezometers measuring the water at A and B. But as soon as you open that valve, there's energy in the system and there's going to be friction in the system. So as soon as you open that valve, you can see that there's more pressure at A than B, because B, there's just more friction has gone through the system, so the water gets slowed down. So that's one other thing to know, is that water flowing through systems is going to experience friction, and the more friction, the lower the pressure is going to be. So I think, let me just see here. I'm just going to go back for a bit here because I forgot. I think I was going to point that out here. So this this problem we had done before, right? It's not showing up. There we go. this problem we had done before. This was, I found this in a textbook somewhere, and it asked the student to calculate the pressure at, you know, A, B, C, D, and all that. And then question B was, what happens to pressure at D when the valve is open? And the answer is that the pressure at E is lower than the pressure at D because of flowing water in the system, and the flowing water has friction on the pipes. So never know, that could be a type of question you could see on the test. Okay, so we're almost done this topic. Just a few other things to kind of discuss. Mostly are kind of like little footnotes. A lot of these things are, okay, just waiting for Zoom to catch up to me. There we go. A lot of these things that we've mentioned are things that engineers would take into consideration, right? All these systems, you know, as environmental technicians or environmental scientists, you guys won't be building these systems, but you might be in charge of, you know, maintaining or monitoring them or whatnot. It's the engineers that have to, you know, they're the people that are thinking about all these systems in terms of, you know, how much pressure is going through it and how much water and volume, and there's actually quite a number of variables that can affect the flow through a system, and there's some of them anyway that is considering. Something else too, right? I was looking through a water quality textbook, and it had, like, I don't know how many pages on pumps. There's different types of pumps, and if you have to work with them, you may have to learn a little bit about them. I can't say I know much about pumps, so I'm not going to really talk about them here in any detail. What else was going to say? Something else with water distribution systems is that a lot of water distribution systems are open as well. If you think about ditches and dikes and things like that. And so there's, you know, I just have this slide here just to say that there's different types of systems that are out there, and but it's pretty much the same principles. Elevation is going to affect pressure and water flow, and then anything else in the system. You can imagine if this was a storm sewer or something like that. These things get clogged up almost all the time, right? I mean, I walk along my street, and in the fall time, you see leaves go in there and all sorts of other junk and garbage, and all of these are going to affect the systems. That's just mentioning gravity, so obviously the slope is going to help things to flow. And I think I mentioned this before as well, that the nice thing about nowadays is we have computers, and so we don't have to usually convert between units if we need, you know, if we need metric units or if we need US units. It's pretty easy to convert on the computer. Usually when you work with a system, you start to get used to the idea of what units you're working with and what's acceptable. So I think I mentioned, for example, the pressure in my car tires is, I think the maximum is 35 PSI or something like that, or the recommended is 35 PSI. So I check my tires, you know, once in a while, and if they're like 33, it's not really a big deal. It gets down to 28, I'm going to add some pressure to it. And then, like I said, same thing when you're working on a job, you get an idea of what the acceptable pressures are going to be, and you start being comfortable with the units too. So I think that's actually the last slide that I have for you guys today. Like I said, mostly just today I want to focus on those two types of calculations. So the pressure calculation in terms of pressure being related to height, and then the water flow equation as well. So this week's lab, you're going to be looking at a couple of those equations, and you're going to be, like I said, the experiment has been done for you already. And what you're going to do is learn how to do some of those calculations in a spreadsheet. So if you have used a spreadsheet before, uh-oh, my phone is ringing. If you have used a spreadsheet before, you'll probably find this week's lab relatively simple and straightforward, so it'll be easy marks. If you haven't used a spreadsheet before, great. You're going to learn some really useful tips on how to crunch data and make some graphs.
Blaine.
Yes.
We're actually for our lab report for the iron lab. We actually do tomorrow. Actually has like supposed to make a spreadsheet like for this lab too.
Perfect. No, that's good. That's good. We've been talking about it for a couple of years. Way back, apparently before I was involved in the program, there used to actually be a computer course that was kind of eliminated, and then as a consequence, we found people had different amounts of comfort levels with using software. So we've been trying to introduce it a bit more, which is why I had been putting in the data analysis in this course. Hopefully you'll find
Yeah,
some
we
use-
were asking Tamar about the opportunities for Excel programs at Keanu.
Yeah, so hopefully you'll find it useful anyway. There's a lot you can do with Excel. I can tell you I use it quite a bit, but I've seen some people that are absolute wizards. They can do so many things. It's really amazing what they can do. We're only tapping a small percentage of its potential. Anyway, that's all for today. I will see you Wednesday. If anyone has any questions about the test after you've done some studying, please get a hold of me. Tomorrow afternoon, I'm relatively available if you want to contact me and go over any questions. We can certainly set some.
In that first slide that you showed, just a general overview of everything that's going to be covered on the next, is that on your slides?